Up to this point in the course, every linear equation that we've studied has only had a single variable, like just an x or just a y. But now we're going to extend our definition of a linear equation out to even having two variables like x's and y's. The only condition is that the variable exponents all have to be 1 if it's going to be called linear. Now let's unpack linear equations in two variables by actually backing up a little bit and refreshing our memory about linear equations in a single variable. That way we can make some observations here. So let's look at this example here. 2x plus 1 equals 7. This is a type of equation that I can solve very easily. We've practiced these a number of times. So to isolate the x, we would subtract 1 from both sides and get 2x equals 6. We'll divide both sides by 2 and we'll get x equals 3. So 3 would be considered the solution to the equation, because if you took 3 and plugged it in for x, it would make the equation true, because 2 times 3 is 6 and 6 plus 1 makes 7. Now let's see if we can extend that idea to an equation with two variables like x and y. What we're going to be looking for now is not just an x value, but an x paired with a y value, that when I plug in both of those numbers, it still makes the equation be true. I'll throw out one as an example. Let's say x was 2 and y was -1. We'll worry about how I got that in a later part of this video, but for now let's just try it. 2 times 2 is 4, that's your x value. 4 minus 5 is -1, and so -1 equals -1, so this would be a solution. But it turns out that equations that have more than one variable have tons of solutions. For example, if x was 3 and y was 1, you can verify this for me, that would be a solution. Or when x was, let's say, 10 and y was 15, that would be a solution. And it turns out you could go on and on and on and on and find solution after solution after a solution for equations that have two variables, for this reason. When you choose any value for x, because there's another variable left, the other variable can be flexible or changed to be whatever you need it to be. So for instance, let's look at this one here. When x was 3, then let's hold off on the y for a minute. 2 times 3 is 6. 6 minus 5 gives us 1. So let's let y be 1, and we have another solution. So these guys have a ton of solutions, where these in just a single variable typically only have one solution. So we're going to label these solutions as what we call ordered pairs. We're going to pair the x with the y that makes the equation true. So for this guy, we found a few different ordered pairs. I think we said 2 comma -1, because 2 was x and -1 was y. I think we said 3 comma 1, and I think we said 10 comma 15, and there are others that I didn't list. So all of these would be listed as solutions. Now that brings up a really good question. How do you show, like if this was on a test, how do you show all these solutions? Because there's so many, surely we're not expected to write them all down. Well, that's exactly true. We have a better way of expressing solutions. Solutions for equations that have two variables are best expressed graphically on an xy plane that we studied in the previous video, the Cartesian coordinate system. So it looks something like this. If you have y equals, let's say, -x plus 3, for example, then we can plot all these x, y ordered pairs on our Cartesian coordinate system, and you'll find something interesting happens. So for this, let's choose a few x's and let's find the y's that complement those x's. Typically we'll choose -2 to 2, but it doesn't have to be negative 2 to 2. You could pick any x values, and you can pick any amount of x values. Now it needs to be at least 2x values, but most people do about 4 or 5 typically, just to get a good range of values. So let's see what these complementary y values are. If x was negative 2, then negative 2 would be positive 2, and 2 and 3 make 5. So the ordered pair, negative 2, 5, that would be one of our solutions. And I can plot that. So how do we plot points? Well, you remember from the previous video, we'll find out where x is negative 2. This is the x-axis. And we'll find out where y is positive 5. 1, 2, 3, 4, 5. Here's the y-axis. And then we'll find out where these points meet in the air. So here's where x is negative 2. Here's where y is 5. So right here would be the point negative 2, 5. All right, let's speed things along for the rest of the points. If x is negative 1, you can check me on this. The y would be 4. When x is 0, y is 3. When x is 1, y is 2. And when x is 2, y is 1. I went through those kind of quickly, but feel free to check me on that and plug in these x's and see what y value you would need to make this equality be true. So let's plot all these. We have negative 2, 5. We have negative 1, 4. We have 0, 3. We have 1, 2. And we have 2, 1. Now you should have noticed something kind of interesting here. For a linear equation, when you plot all of these solutions, they line up in a straight line. And now it's pretty clear to see why we call these guys linear equations. The reason for that is because when we graph them on a two-dimensional plane, they make a line. That's why we call them linear equations. If this equation was not linear, let's say it was like y equals negative x squared plus 3, and it violated the definition of being linear, it wouldn't be a straight line anymore. So as long as these exponents are 1 and you don't have any variables in the denominator, you'll get a straight line like we have here. So anyways, that's just a little introduction to linear equations in two variables. We'll have a number of videos in upcoming that will unpack a lot of stuff about linear equations in two variables, such as how to graph them and all sorts of different properties relating to linear equations.